All right, in this video, we learn how to solve exponential equations with logarithms. So for our warm-up, a quick review on converting from exponential form to logarithmic form. So let's go through these. So in the first one, the exponential term has already been isolated. It's the only term on that left side. So I know my base is 4. So I'm going to start by writing log base 4 of the result 16, and then this equals the exponent of x minus 8. For the second equation, we have to start by dividing both sides by 3 so that we isolate this exponential term. So I want to cancel out those 3's. 72 over 3 is 24, so I have 10 to the power of x squared equals 24. So we have log base 10, but that's a common log, so I'm not going to write the subscript of 10. This is log of 24 equals x squared. And then the third equation, e is the base, so that means I have to use natural log, which has a base e. Natural log of 5 will give me 2x. Okay, and the question 2 is asking you, how do we, if we continue to solve each equation, what would happen? Is using logarithms the only way to solve them? So if we go ahead and keep solving, in other words, we're getting x by itself. Over here, I just have to add 8 to both sides. So my solution is log base 4 of 16. And then I'm adding 8 to that term. This gives me x, which is a solution. For the second equation, I would just have to square root both sides. So I get that x is equal to plus or minus log of 24. And then third equation, just divide both sides by 2. So the main idea here is that logarithms can be used to essentially get the exponent with the variable down to ground level. And then from there, you just apply the inverse operations to solve the equation. So you undo subtraction through addition, you square root both sides, whatever you got to do to get x by itself. But it's only possible to solve for x if we use a logarithm to undo that exponent. Because remember, logarithms and exponentials are inverses of each other. They undo each other. So by using logs, we can undo the exponent and then apply inverse operations to solve for the variable. So let's see another example. So when solving exponential equations with logarithms, there are really not really two methods, but two perspectives that ultimately give the same solution. So perspective 1 is what we did in the warm-up. We converted to log form. So as long as my exponential term has been isolated, I can convert to log form, right? I got base 2, so I have log base 2 of 30 equals x. And that's it. That's my solution. And notice that using logs was a requirement for this because 30 is not power of 2. Now in the warm-up, I just want to quickly highlight in this equation, you may have noticed that 16 is a power of 4. So you may have rewritten the equation as the right-hand side becomes 4 squared. And then you can actually set the exponents equal since the bases are the same, and solve and get that x is 10. So that equation was possible to solve without logarithms, but notice that logarithms still get us to a solution, even though it's not fully simplified. Like log base 4 of 16 is actually 2, because 2 to the 4th is 16. So you can simplify it further. But in this example, perspective 1, log base 2 of 30 cannot be done mentally. You would need a calculator for that. But converting to log form works really well as long as the exponential term has been isolated. Now, perspective 2 is what appears in textbooks. And when you have exponential functions on both sides of the equation, this other approach is actually more mandatory. But I still want to show it to you even in this problem. So instead of converting to log form, I mean, that's essentially what's going to happen. But we're going to frame it as we're taking the log of both sides. So what do I mean? Well, first we have to go over the power rule of logs, which we will come across again later, but is part of this perspective. And so the power rule of logs says if you have the log of x to the p power, or I'll use b for base. be consistent. If I have log of b to the p power, then essentially the logarithm, remember, it undoes the exponent. So the exponent gets brought down in front of the log. So essentially you're taking p and you're moving it in front. So you have p times log of b. So in this equation, when you take the log of both sides, you know, what you do to one side, you got to do to the other side, right? So I'm taking the log of the whole equation. And so my exponent gets brought in front. So I have x log of 2 equals log of 30. And then to solve for x, there's multiplication over here. So I just divide by log 2 on both sides. And so this would be my solution since these cancel out. So notice that log of 30 over log of 2 is actually equivalent to this expression by the change of base formula, which I highlighted in class. You can check with a calculator that they would that both expressions would give the same decimal answer. So that's one perspective that I figured I'd show you, and you may prefer it better, especially since notice that my answer here is in base 10, and so I could actually put this in a calculator and check my answer since calculator only allows base 10. So speaking of which, we should check our work. I'll only do it for the first perspective to save some time here. So I have 2 to the power of log base 2 of 30. And I'm checking to see that this equals 30. Well, by the inverse property of logarithms, these bases will cancel out. And so you have 30 equals 30. So yes, our solution makes sense. So in here, practice A, you get used to solving exponential equations with logarithms. I won't do these for you, but I will quickly mention that you need to make sure the exponential term is isolated, meaning no coefficient in front other than 1, and you have to undo any adding or subtracting. So over here, your first step would be take away 11 on both sides, you do the rest. Over here, divide both sides by 2. And now you convert to log form or take, in this case, the natural log of both sides. So you have to make sure your exponential term is isolated before you apply logarithms. Now, some exponential equations appear in quadratic form. So let's go through an example of that. So I have 2 to the power of 2x plus 2 to the x minus 12 equals 0. So this looks like a quadratic. We have something squared, kind of. There's, I mean, not really a linear term, but plus 2 to the x. So we can actually treat this like a quadratic equation, meaning we can see if we can factor it somehow. Now, you may be looking at this and getting kind of nervous because, well, this is not the kind of quadratic that you're used to seeing. And so what we can do is rewrite this equation in a way that is more familiar to us, and it will make factoring a lot easier. We're going to use a method that is called U substitution. So what is U substitution? U substitution says we're going to take part of the expression on the left. We're going to let U, we're going to make a declare that U is equal to 2 to the x. Now, why am I doing this? Why am I letting U equal 2 to the x? Well, let's see what happens when I substitute U in for every 2 to the x that's there. So a quick note, this particular term, 2 to the 2x power, is the same as 2 to the x squared, because by the power to a power rule, you would have to multiply the exponents. And so I write it in that form to show you that 2 to the x is in that term. It's also in this term. It's appearing twice. So the equation becomes U squared plus U minus 12 equals 0. Now that should look more comfortable. Just a single variable is being squared, and then, right, it's like U is like X. It looks a lot more like this standard form, AX squared plus BX plus C that we're used to seeing. It looks very similar. And now we know how to handle this kind of equation. We can factor it. This is U plus 4 times U minus 3 equals 0. And so u equals -4 or +3. Now we're not done yet because we have to solve for x. What we just did is solve for u. But remember, u is equal to 2 to the x. So guess what? Either 2 to the x equals -4 or 2 to the x equals 3. Okay, so I went backwards. I remember that u is equal to 2 to the x. So if u equals -4, that really means 2 to the x is -4. And if u equals 3, then 2 to the x equals 3 because u equals 2x. They are the same. I can swap one for the other. And now you have to solve these two exponential equations like what we did on page 1. This first equation has no solution. Why? Because you can't raise you can't raise a positive base to a power and get a negative result, as we discussed before. So that particular equation doesn't give us anything. What about the other one? 2 to the third power equals 3. Well, that's definitely going to have a solution. We can just write in log form, log base 2 of 3 equals x. And that is the only solution. You can substitute it back in to check your work, but that will be our only solution. Okay, so to summarize this procedure, when you have an exponential equation in quadratic form, I recommend doing u substitution because it turns into a quadratic equation that you're more used to solving. You may elect to solve this equation without u substitution, and that's certainly possible, but I want to emphasize this u substitution because it brings back ideas that you've seen before, and so I think you should consider doing it that way. There are some practice problems down here. Again, I'm not going to do these for you, but some of them look a little different than the example I showed. So to show you what I mean, like in this equation, there's 3 to the x here, but I don't see 3 to the x in this term like in the example. However, keep in mind 9 to the x can be rewritten as 3 squared to the x. In fact, I'm actually going to, well, okay, you would start with that, but then I want 3 to the x. So you can swap the order of the exponents because multiplication can happen in any order. It is commutative. So if you rewrite the first term as 3 to the x being squared, because that's the same as 9 to the x, then you have -5 to the 3x power plus 6 equals 0. Now you can go ahead and say that u equals 3 to the x. And from there, you can follow the example I showed. Okay, so yeah, solving these pseudo quadratic equations is what they're called. They're a little odd to see at first, but once you practice it, with the u substitution and all, you will be more comfortable with it. And in tomorrow's class, we're going to practice this a lot, some more. All right, yeah, pseudo quadratic equations pop up often. So we're seeing it for the first time here. In trigonometry, we're going to actually solve some more of these equations. So it's good to see this u substitution technique. So that is all for this video. Thank you for watching. Go Writers.